I am going to work out 3 problems that are KSP type problems, and they represent the 3 different types of questions you can and will be asked about KSP. So the first is gives you the solubility of the various ions and asks you to calculate KSP. The second type gives you the KSP value and asks you to calculate solubility. And the third one mixes 2 different ionic compounds together and asks you whether or not a precipitate will form. So here's the first one, which is probably the easiest type. So what I would recommend doing is listen to this first one, go back to the worksheet I posted and try to do a couple of them on your own, and then go on to the next type that's a little bit more difficult. All right, so the first step of any KSP problem is to write out the equilibrium. First step of any equilibrium, actually. So the equilibrium in this case is the solubility of what we have formerly called an insoluble ionic compound. Now we know it's really a partially soluble ionic compound. So anytime an ionic compound dissolves in water, it dissociates into the cations and the anions that make it up. So in this case, we have 3 barium ions. You need to remember your ionic charges. Barium's in group number 2, so it has a charge of +2. If you're fuzzy at all about these charges, you want to refresh on them. So you probably need a periodic table out in front of you as well as a polyatomic ion list. And then there are 2 phosphate polyatomics. So as you notice, the subscripts become coefficients when they separate into the ions. So we have 2 phosphate ions. Phosphate has a charge of -3. Okay, so remember your charges. So there's the equilibrium. Now remember, if you have an ionic compound that's totally soluble, there's no equilibrium. It just completely 100% dissolves. So we only have equilibrium problems with slightly soluble or, quote, insoluble ionic compounds. All right, so the first step is always to write up your equilibrium. The second step is to always write up your KSP, or equilibrium constant expression, and you'll get partial credit for those 2 things, even if you don't know how to solve the problem. So remember, KSP, or any equilibrium constant, is concentration of the products, okay, raised to the power of whatever their coefficient is. And KSP never has a denominator. So let me go back now, in case you missed the lecture. If it's an insoluble or partially soluble ionic compound, most of it's not dissolved, and so it's termed a solid when we put states of matter. Solids are never included in equilibrium constants, so that's why KSP problems will never have a denominator. Now, if I included all of the states of matter here, I really should have put AQ for aqueous next to the 2 ions. Okay, they are dissolved and floating around in the water. All right, so here's our KSP expression. They didn't give it to us in this point, in this problem. We're trying to solve for it. Do not get KSP mixed up with solubility. KSP is not solubility. They are not the same. Solubility is related to the X factor that we deal with in our ice tables. All right, so let's write out the ice table for our equilibrium. I like to write the equilibrium right on top of the ice table. It just kind of helps me keep straight what's what. All right. All right, so since the original slightly soluble salt does not affect the equilibrium, I'm just going to put a big X there in my ice table, and I'm going to focus on these 2. In the beginning information, I know that the solubility of barium phosphate itself was 1.4 times 10 to the minus 8 molar. What the heck does that mean, the solubility? That means that that's how much of the original slightly soluble salt dissolves. So now when you're dealing with solubility, we're going to call that X. Okay, remember I said solubility is related to X. So if we call the solubility of barium phosphate X, what would the solubility of the barium ion be, or the concentration? Solubility and concentration are really kind of the same thing. So then the barium would be 3X, and the phosphate ion would be 2X. Okay, so we know that the initial concentration of both of these ions is 0, right? And this might be easier doing it this way. So the change in the concentration is 3X for the barium ion, 2X for the phosphate ion. So the equilibrium concentration for the barium ion is simply 3X, and for the phosphate ion, 2X. But now I know something about X, okay? I know that X is 1.4 times 10 to the minus 8. So I'm going to go back to my equilibrium expression, equilibrium constant expression, and I'm going to plug in these values and you'll see how we work it out. All right, so our equilibrium expression looks like this. I'm going to go ahead and plug the X values in just so you can kind of see how you work out the math here. So in terms of X, we called barium 3X. Okay, you're going to feel like you compensated for that 3 coefficient of barium 2 times, and I guess in a way you did, but you're going to find that your exponent tends to equal, well, does equal the coefficient you have here. So don't be tempted to drop one of them. You need them both. Okay, and then concentration of phosphate was 2X. And again, don't forget this squared. All right, so now what do we know? We know that X equals 1.4 times 10 to the minus 8 molar. Okay, so let's plug this into the Ksp value. So Ksp, so 3X is 4.2 times 10 to the minus 8. Again, don't forget that cube. All I did there is multiply this 1.4 times 10 to the minus 8 by 3. Okay, 2X is 1.4 times 10 to the minus 8 times 2. Okay, 2.8 times 10 to the minus 8 squared. All right, so this really isn't a hard problem. There's just a lot of places to make an error. So let me go ahead and crunch it into my calculator and hope and pray that I get the answer on the answer key. So 4.2 times, times 10 to the minus 8 cubed is 7.4 times 10 to the minus 23. Wowee. Okay, and let's see, 2.8 times 10 to the minus 8 squared is 7.8 times 10 to the minus 16. All right, so then if I multiply these two teeny tiny numbers together, I get that Ksp equals 5.8 times 10 to the minus 38. Oh my, that's awesome. That actually matches the answer. Amazing, huh? All right, so let's move on to the next problem. Oops. And I take it back, it may not be a little bit harder. This one was a little bit tricky. So here we go. All right, this is number 12 on the practice worksheet I posted in the practice problem folder. And it's asking, instead of asking for Ksp, it is asking for the solubility of the slightly soluble salt silver carbonate. So again, when you see the word solubility, write yourself an X to remind yourself that solubility is a concentration factor, which is represented by X in our ice tables. So again, as always, the first thing you want to do is write out your equilibrium. Okay. Since silver carbonate is insoluble or slightly soluble, we're going to call it S for solid. It dissociates, or when it dissolves, dissociates into the cations and anions. There are 2 silver ions. Silver always has a charge of +1. That's soluble, so there's an AQ aqueous. And there is 1 carbonate polyatomic. Carbonate has a charge of -2. The Ksp expression would be, let's see, concentration of the silver ion squared, because there's a 2 coefficient in front of the silver, times concentration of the carbonate ion. And there's only one of those in the balanced equation, so I have just an exponent of 1. And we are given Ksp, 8.1 times 10 to the -12. So now I need to get the concentrations or the solubilities of the silver ion and the carbonate ion. All right, so ice table. Okay, the slightly soluble salt is considered a solid, so it's not included in the equilibrium calculations. And the original concentration of the ions is 0 until some of it dissolves. Change, as always, is the important row, and that's the row I need to pay attention to the coefficients. So let's see, I'm going to call the change in the silver ion concentration plus 2x. And for every 2 silver ions that are formed, there's only 1 carbonate ion that is formed, so I'm going to call the carbonate change 1x. So the equilibrium expressions of the 2 ions are simply 2x and x. Remember that the equilibrium expression was concentration of silver ion squared times concentration of the carbonate ion. So plug in what you got for equilibrium concentrations. Silver is 2x. Do not leave this exponent out. And again, notice you're going to have the coefficient 2 times, but that's fine. That's the way it's supposed to be. Concentration of carbonate at equilibrium we're going to call x. And we were given the equilibrium Ksp value. And it was 8.1 times 10 to the -12. So now we need to solve for x. All right, so solving for x. 2x squared is 4x squared. Okay? And so that gives 4x cubed. 4x cubed is a very common expression to solve for x in Ksp problems. Don't forget to square this too. That's probably one of the most common mistakes. So 4x cubed equals 8.1 times 10 to the -12. In order to solve for x, you need to divide both sides by 4. And so x cubed equals 2.03 times 10 to the -12. And cube root of both sides is x equals 1.323 times 10 to the -4. Remember, x is always a concentration term, so I'm just going to put the m there. Now, don't stop here. It's very tempting to say, okay, I'm done. Go back and see what the problem asked for and make sure, actually write out the answer, okay? This problem is asking for the solubility of the original slightly soluble salt. I wondered if my dogs were going to make a debut in this. Okay, so the solubility of silver carbonate okay, is 1.3 times 10 to the minus 4 molar. That's how much of it dissolves in water. And that is, in fact, the final answer. This is the third and last problem I'm going to work out for KSP, unless you have a specific one you have a question about. This is probably the most difficult of the KSP. Again, once you understand it, it's really not that difficult, so I don't want to scare you. But it asks about a precipitate, and it's mixing two different ionic compounds together. So let me just take a minute and make sure you understand the concept of what's going on here. You're mixing two relatively soluble ionic compounds together, and the presumption is you're going to make a new ionic compound that is relatively insoluble. That's typically how these problems work. So the first thing you need to do is write out a double replacement reaction and determine what is the unsoluble or the insoluble ionic compound that this reaction is going to make. So in a double replacement reaction, which if you're fuzzy about, you need to refamiliarize yourself with it, the two outer ions are going to end up together and the two inner ions are going to end up together. Okay. Remember that the metal is always shown first in a chemical formula. So I'm going to have lead iodide, I'm not balancing charges yet, and sodium nitrite are going to be my basic ions. Then you need to assign charges to the individual ions so that you get the chemical formula correctly. Lead acts like a transition metal, and we can tell in this particular problem that it's lead with a charge of +2, because we hopefully know. Get your polyatomic ion list in front of you if you don't remember charges. Nitrites have a -1 charge, and there are two of them, which means lead has to have a +2. Halides, iodide is -1. So the correct formula for lead iodide in this problem is PbI2. All right, sodium has always, it's in group 1, charge of +1. Nitrate has a charge of -1, and so these are present in a 1-to-1 ratio. And so you probably don't really need to balance it for this particular problem, but just because I can't stand to see an unbalanced reaction, I'm going to. So I need to put a 2 there and a 2 here. All right, so which of these products, and this, hold on, let me get my dog. This is where you need your solubility chart, okay? And what you will see from your solubility chart is any ionic compound that has a group 1 metal is automatically soluble. So sodium nitrate, aqueous, totally soluble, so there's no equilibrium, it completely dissolves. Lead iodide, you will notice from your solubility chart, if you don't have one in front of you, you need to get one. I'm going to let you use a solubility chart for your quiz, but I am not going to print them out for you. You need to have one available. Maybe I will print one out. We'll see. Anyway, get one. So even though halides are typically soluble, lead is one of the exceptions that make them insoluble. So lead iodide is an insoluble ionic compound, and therefore lead iodide can potentially make a precipitate depending on how much of it is there, and lead iodide is the appropriate equilibrium expression that you need to write for this problem. So all of that is just to determine that lead iodide is the one that is forming the equilibrium. So let's go ahead and write out that equilibrium. It, as always, when it dissolves, it dissociates into the cations and anions. Oh my. There goes my doggies. All right. All right, so this is where I noticed that this particular worksheet does not always give you the value of KSP. Every KSP problem needs to give you some known value, either the value of KSP or the solubility value of one of the reactants or products. So I went ahead and uploaded a table of KSP values on D2L for you to use in solving the rest of these problems, and I will give the KSP value for lead iodide to you right now. So KSP for lead iodide is 8.5 times 10 to the minus 9, And remember our Ksp expression was concentration of the lead ion times concentration of the iodide ion squared. And now, what does this mean exactly? This means that whatever the concentration of lead ion is in solution, multiplied by whatever the concentration of iodide is in solution squared, better not exceed the Ksp value, 8.5 times 10 to the minus 9. 8.5 times 10 to the minus 9 is the maximum amount that lead and iodine can combine to be soluble. So we need to plug in the values for the lead ion and for the iodine ion and compare this value we get to the Ksp. If this value, which we'll call Q, that's the concentration we have now, is greater than the value for K, that means that a precipitate will form. That means there's too much dissolved. If the Q value we get is less than the value for K, then it'll all remain dissolved. It means we haven't exceeded. So let's go ahead and plug in those values. How the heck do we figure out what the concentration of the lead ion and the iodide ion is? I want you to take a minute and go back and read the question slowly. And from doing that, you can tell that the lead ion, the source of the lead ion, comes from lead nitrate. So if you go back and read the problem, you can see we added that. That is totally soluble. So however much we started with this, all right, so going back to the problem, it told us that we started with 65 milliliters of lead nitrite and that the concentration of that 65 milliliters was 0.015 molarity, which remember just means moles per liter. All right, and so from that we're going to find out what the concentration of lead ion was, because it all comes from this, which is totally soluble. And the source of the iodide ion comes from sodium iodide, which again is totally soluble. It's got a group 1 metal. And how much of that did we add? We added 45 milliliters of sodium iodide, and the molarity of the sodium iodide was 0.015 molarity, moles per liter. Okay? So from these two quantities given in the problem, we can figure out how many moles of lead and sodium were added. Well, actually the concentration of both of them, plug them into our Ksp expression, and then see how much we have dissolved, whether it's too much or whether the solution can handle it. So let's go ahead and go through the calculations on the next page. So let's do lead nitrite first. Lead nitrite, I keep losing my place, there it is, 65 milliliters, so I'm going to change that into liters, of lead nitrate times the concentration, which is 0.015 molar, okay, will give us how many moles of lead nitrate was added. And so let me calculate that real quick. Okay, 0.065 times 0.015. All right, so we have 0.000975 moles of lead nitrate that were added. So since for every one lead nitrite we add, we get one lead ion, okay, that's totally soluble. That means that the moles of lead ion I have in solution, 0.000975 moles, okay? But I need concentration for my Ksp value, so I need to know the total volume of the solution. Well, I started with 0.065 liters of this particular solution, but remember, I also added a second solution, and that second solution is sodium iodide. So we've got to take that volume into account also. So let's go over our information for sodium iodide again. And let's see, there were 45 milliliters, so that's 0.045 liters of sodium iodide solution. And the molarity of that was also 0.015. So the moles of sodium iodide added to that solution are 0.000675 moles of sodium iodide. Again, for every 1 sodium iodide I add, I get 1 iodide ion. There's a 1-to-1 relationship between these two. All right, so that means that the moles of iodide are also 0.000675 moles of the iodide ion. All right, so the concentration of lead ion then is 0.000975 moles divided by the total volume, which is 0.110 liters. And the concentration of the iodide ion is 0.000675 moles, again divided by the total volume of those two solutions when they're mixed together. And let's see what those values are. All right, so the concentration of the lead ion after mixing those two solutions is 0.0089 molar. The concentration of the iodide ion is 0.0061 molar. Right? What do I do with those? I plug those back into the Ksp expression. I'm going to call this Qsp because I don't know that I'm in equilibrium. Anytime you're not sure if you're at equilibrium, you call it Q instead of K, and then you compare the value you get to the known Ksp. So the Qsp or the Ksp expression looks like this. Okay? And plugging in those values would be 0.0089 times 0.0061 squared. And that would give me a total Qsp value of 3.3 times 10 to the minus 7. Remember that K and Q values are unitless, so we don't need to worry about a unit. What we do need to do now, this problem gets kind of lengthy, is we need to compare this Q value to the K value. So what was Ksp for this? And that's the one you have to refer to the Ksp chart that I uploaded for you on D2L, because this problem should have given it to you, and it did not. So the Ksp value is 8.5 times 10 to the minus 9, and the Q value 3.3 times 10 to the minus 7. Which is larger? Well, minus 7 makes it win. That is the larger value. So what that means is that Qsp is larger than Ksp. What does that mean? That means that we have too much product, in this case the ions, too much of the ions dissolved. And that means that we are going to get a precipitate. All right, so let me just summarize Q and K again. Anytime that Q is greater than K, that means there's too much product. Okay? In the case of a Ksp problem, that means that a precipitate will form. Okay? If Q is less than K, that means that more product will form before equilibrium or to reach equilibrium. It means everything that's formed now is in solution and more can dissolve. And that means in the case of Ksp problems, no precipitate will form. All right. So these are the harder problems. To be honest with you, I'm not going to put a precipitation question on your Tuesday quiz. However, there will be one on your test, and it'll probably be a good free response question. So you do need to learn to work these precipitation problems out. But that's it for today on the problems.